Hey, we're live. Welcome back, Verge.
Welcome back, Mark. We've got another fun-filled day of calculus for everybody. I'm so excited. It's one of my favorite topics.
All right, I am Mark Corelli from Ryan High School in Denton, Texas, and
I'm Verge Cornelius from Lafayette High School in Oxford, Mississippi.
All right, here's our schedule again. We are down here on, is it Thursday, April 16th?
That's correct.
Doing Unit 4. Tomorrow we're going to do mixed bag review, and then we will continue our review through May 1st. And again, you can come back and freeze this. The QR code does work on a smartphone. Just aim your camera at it.
And I can verify I tried it and it worked. It was wonderful.
Yay. This is the website that AP is set up. You got to dig around in it to find the information, but here's what we think is important. May 12th, 2 p.m. Eastern, same time as our lesson today, just on a Tuesday. 45-ish minutes, the way they add that up, 25 and 15 with 2 5-minute upload periods. And day 5, that's a work week.
Yeah. And we're not even adding in the weekends there. We have had no mistakes, apparently, that we have found, or anybody else anyway.
That's right. That we've paid attention to. Spam. All right. So we have done our introductions. We are about to do our warm-up. Unit 4 review is contextual applications of differentiation. So basically taking Tuesday and Wednesday and applying it to applications. And then we'll wrap up and let you know
quote unquote real life problems that are slightly sanitized.
Completely set up. And we will also be letting you know what's in that Dropbox. It's already in there for today and Tuesday, which was basic differentiation. The relevant keys are in the Dropbox for that already too. So.
Yeah, and there is a notes page that's in the Dropbox in case you want to print that and follow along when I do the notes. But the warm-ups are not in there on the notes page, so we're just going to go ahead and start with that. So here's our warm-up for today. This is always a fun conversation that Mark and I have pretty much immediately after the lesson. We talk about what should we do for our warm-up, you know, blah, blah, blah. And so we had a couple of ideas we were tossing around, but we wanted to do this one. So you're given x squared plus y squared equals 39. And you have to find 3 things. First of all, you have to find dy dx, you have to find dy dt, and then finally, for what values or value of x does the graph of x squared plus y squared equal 39 have a horizontal tangent?
And both 1 and 2 will be symbolic answers. Those will not be numerical. So.
Okay, good. So you can pause the video right now and work those problems. I think that would be a good thing to do. I'll tell a joke. By the way, I'm kind of running out of jokes. So if anybody wants to send me any jokes, I'll be happy to review them anyway.
Yes.
All right, here you go, Mark. What kind of food do math teachers eat?
I'm trying to think if I've heard of this one. What kind of food do math teachers eat, Verge?
They eat square meals, of course.
Okay. I've heard a variation of that. Because you've got why was 6 afraid of 7?
Uh-huh.
And that was why did 7 eat 9? Because he gets 3 squared meals a day.
Oh, that's so cute. Yeah. Okay, so I'm going to go ahead and I'm going to project my overhead for a little while anyway, because I'm going to go over the warm-up with Mark helping, of course, making sure I'm not making any mistakes. And then I'm also going to so here we have it. So we've got x squared plus y squared equals 39. We may or may not recognize what that is. It doesn't matter. We're just going to use implicit differentiation to figure out dy dx. So the derivative of x squared with respect to x is going to be 2x, plus the derivative of y squared with respect to x is going to be 2y dy dx is equal to the derivative of 39 with respect to x is going to be 0. So I'm going to subtract 2x from both sides, divide both sides by 2y, and I wind up with dy dx, like Mark said, is negative x over y once I divide both sides by 2. Secondly, here I need to find dy dt. So now I'm differentiating with respect to not x or y, but I'm introducing a third variable, t. So when I differentiate x squared with respect to t, I'm going to wind up with 2x dx dt plus derivative of y squared with respect to t is going to be 2y dy dt. And then still the derivative of 39 is 0. And now I'm solving for dy dt. So I'm going to subtract, and I'm going to actually show it on this one, subtract 2x dx dt from both sides. So I have 2y dy dt is equal to negative 2x dx dt. And then divide both sides by this 2y. So those 2's kind of cancel out. So I get negative x dx dt all divided by y. Any comments on that, Mark? Looks good?
Yep. Of course, that dx dt can be out back, right? That you could just have the negative x over y, and fractions allow a lot of freedom for how that can be written. So.
Oh, when he says out back, I was imagining like a nice steakhouse dinner or something like that. Okay, this is what he means by out back.
It's funny. I catch, I try to like keep I'm the one of technical voice, right? Occasionally, where I'm like, we should say it this way, except when I talk about fractions, numerator, denominator, out back, out front.
Yeah. So here he means it's like tacked on at the end instead of up in the number topinator. Is that what it is?
Numatoperator. It's just a subliminal way of saying numerator and sliding the word top into it.
Okay. Then the question was, what are the x coordinates of the horizontal tangent or tangents? Now, if you really know what you're looking at, you don't need calculus to answer this question, because what is it that we're actually looking at, Mark? What is this the equation of?
That looks a lot like a circle centered at the origin with a radius that I don't like, but it's probably 3649, so between 6 and 7. Maybe 6.3.
Okay, so yeah, so the radius is the square root of 39. And it's funny that you say you don't like the radius, because you actually picked this number yesterday. I wanted to put 36 and you changed it.
I was 600ths high at 6.24.
Okay, so this right here would be a place where I would have a horizontal tangent, because I've got that horizontal line right there touching in just one spot. And then I've got the horizontal tangent there as well. So in both of these spots, the x value is equal to 0 without calculus. Okay, can really be done without calculus. However, if I've got a horizontal tangent, what does that mean my slope is equal to? It means my slope is equal to 0. So I could set dy dx equal to 0. And I had found that dy dx was equal to negative x over y. So when I solve this equation right here, I end up with x equals 0.
Yep.
So that's a nice little problem.
You could also, just to make things even more complicated, you could set dx dt equal to 0 as well. Because, or no, dy dt, sorry. Yes.
dy dt.
dy dt equals 0, because you could do dy dx as dy dt over dx dt, which is a little preview for AB students, or a review topic for BC.
Thinking about what that could be. Oop, not that yet. Not that yet either. How about this? All right. So here's here's our Unit 4 review, if you've taken a look at the notes page. I just kind of typed this all up from what the College Board has provided in terms of the order that they would teach it in. Of course, teachers can teach this in any order that they want. A lot of these are somewhat standalone topics, but for each of these topics right here, we're going to just kind of do one example of each, just to kind of refresh your memory on it. So for this first topic right here, interpreting the meaning of the derivative in context, this is a really nice example right here. It says the function c of x gives the cost of digging a hole x feet deep. We found this in the AP classroom of some sort. I think it was pretty much exactly like this. The function c of x gives the cost.
I think this was in teacher resources, though, not in the question bank. So
that could be, yeah. The function c of x gives the cost of digging a hole x feet deep. C of 20 is equal to 140 means that a hole, how many feet deep, costs how much to dig. So let's think about what these numbers mean. A hole, x feet deep.
X is the hole, yeah.
Yeah, so 20 feet deep costs $140 to dig. That's not calculus.
It is math,
That's algebra
though.
one. It is. I
Because I
teach it in
do
algebra
have
one.
kids who go, I do have students who, they say, oh, this isn't math. I'm like, no, actually, this is math.
Yeah, in fact, this is important that you can distinguish between prior knowledge versus now I see this C prime. So C prime of 20 equals 5. What does that mean? How can I interpret that in the context of this hole digging situation? C prime of 20 equals 5 means that when the hole is 20 feet deep, I guess I got to write the word deep there. The cost of digging is doing what? Increasing or decreasing?
Well, it's positive.
When you say it, which it are you
That's an
talking
excellent
about?
point. Well, they both are, but I'm referring to the 5, which is equal to our derivative.
Right. Cost of digging is increasing at a rate of $5 per foot. So now this C prime of 20 equals 5 is really giving us a rate at which something is happening. And I'm very careful to make sure my units are correct on that when I'm talking about it. The bigger the hole, the more expensive the project's going to be, especially as you get further down. I mean, that makes sense to me. Go ahead, Mark.
It makes sense to me. I'm going to steal the screen just for a second and just say, we talked yesterday about internal dialogues and thought bubbles and keeping track of what's my independent variable, what's my dependent variable, what's going on. This has been ingrained into you guys for, oh gosh, 2/3 of a year now almost. And so this is pretty reflexive that y equals f of x and that, y prime is dy dx, which is f prime of x. So what I do with my students when they're like, well, I don't remember which is which, these are both x, right? Because c of x becomes c prime of x. So I know that those units had to stay the same. But then this dc dx is your units for your rate because it's c was cost and x is feet. So that's dollars per cost right there. And there is no shame in going off to the side and doing that, right?
Yeah, I think that's a good point, and I probably went over that too quickly. I'm glad you interrupted me on that because we don't want to introduce some new units that weren't really in the problem. Like we don't want to say like $5 per day or $5 per hour or something like that, assuming that it's some sort of a related rate problem that has to do with time.
Or feet per dollar or anything like that.
So. Yeah, exactly. Okay, so good. 4.2, this one was all about straight line motion, connecting position, velocity, and acceleration. We did a ton of this in our 8.2 video, and I looked back and saw when that was AP Live number 10. So there's a lot of really good derivatives of position, velocity, acceleration that if you haven't yet watched that video, that's really key to watch that video. There's not that much anti-differentiation in it, honestly. It's more of the derivatives. But in any case, here's just a sample problem. A particle moves back and forth on a horizontal track for t in between 0 and pi over 2 minutes, where t is equal to 0 but not equal to pi over 2. The particle's position in feet is given by the function s of t equals 1/2 tangent of t. Find the acceleration of the particle at time t equals pi over 6 minutes and indicate units of measure. So when you have position, to get to acceleration, how many times do you have to take the derivative?
Well, the first derivative of position will just be change in position with respect to time. So things like, well, in this case, feet per minute, that sounds like a velocity. Yeah.
Exactly. And then we'll have to take the plan is, then we would have to take the derivative of the velocity, and then we would know the acceleration. So here, when I take the derivative of 1/2 tangent t, I just am really focused on taking the derivative of tangent t, which is going to be secant squared t. And that ties back to what we did on Tuesday for sure. And then the second derivative here of position is going to equal the derivative of velocity is going to be my acceleration that I'm looking for. And this I really need chain rule for, because this is secant t to the second power. So now I'm going to go ahead and do that power rule chain where I've got that inside function as a secant function. So 2 times a half is 1. Secant of t to the 1 power. I'm not going to write it, I'm just saying it. And then times, because otherwise it's going to get too confusing.
Secant prime, what is that? Yeah.
Right, exactly. Times the derivative of what's inside. The derivative of secant t is going to be secant t tangent t. Lots of t's in here. Make sure you have tails on your t's so that you're not confused. So then a of pi over 6 is going to be secant of pi over 6 times secant of pi over 6 times tangent of pi over 6. And then
I did this one with, I was just gonna say, I did this without a calculator when I was typing up the key yesterday. But man, did I double check myself. Those secants are like, okay, so it's really cosine, but it's inverted.
Yeah, so secant is the reciprocal of cosine. And so the cosine of pi over 6 would be root 3 over 2. And so now this is going to equal, and I apologize, I'm running out of room. Maybe I'll just fold this paper in half. That's pretty sweet. Okay, so then we have root 3 over 2 times root 3 over 2 times the tangent of pi over 6 is going to be a half divided by root 3 over 2, or sorry, these need to be reciprocals. I said it and then I didn't do it. Right, Mark?
Yes, sorry. We just had
laughing.
It's fine. My wife's just apologized. We just had a UPS delivery or something, and
so
my dog was. I had my mic muted because my dog decided she wanted to.
Okay, so we have secant of pi over 6 is the reciprocal of the cosine of pi over 6. So that's going to be 2 over root 3, and then times another 2 over root 3, and then times the tangent of pi over 6 would be a half divided by root 3 over 2, or 1 divided by root 3. You can really leave it just like that, or you can write 4 over 3 square root of 3. You know, any of these.
There's a lot of ways to write it.
Happy answers, yeah.
And actually, on AP, you can stop at the secant pi over 6, secant pi over 6, tangent pi over 6. That's actually considered a numeric answer in the AP exam. My basic rule of thumb for that is if you could put it into a small scientific non-graphing calculator, you can stop.
Good tip. All right, 4.3 was rates of change in applied contexts other than motion. And I just took a problem that was a quasi multiple choice problem and made a little matching exercise out of it. It says if P of t models the size of a population at time t is greater than 0, which of the following differential equations describes linear growth in the size of the population? So if growth is linear, then that means the original function would have been some sort of y equals mx plus b. I'm just going to jot that down somewhere. Or in this case, p is the P seems to be the dependent variable here. So it would be P instead of Y and then equals. Well, the derivative of a linear function would just be a constant. So the one that's linear growth would have to be dp dt equals 200. Which describes the exponential growth? Well, the exponential function, when you take the derivative of it to figure out the rate, is really itself when you take the derivative of it. Maybe times, you know, the derivative of the exponent if there's a chain rule going on or something like that. But which one of the remaining ones has that as a feature? It's this one, dp dt equals 200p.
You should definitely rule out the second and third one right away because they're obviously polynomials, right?
That's right. So those are good ones to kind of think about the structure, especially if you've been with us all the way since Unit 7. We just spent a lot of time talking about this one.
Yes.
So.
And we actually included the linear in there as well. So.
We did. Yep. All right. This next one here was kind of like the introduction to related rates. And this little problem I wrote for 4.4 says determine dz dt if you know that z is equal to xy squared. So that's z is equal to xy squared. My printer is not the greatest. And then z is equal to 3, y is equal to a half, dx dt is equal to -2, and then finally dy dt is equal to 5. It's a great little question that really tests a lot of different skills. First, you have to know how to do implicit differentiation, which is basically chain rule. Second of all, you have to know how to do product rule. Okay, so implicit differentiation is going to happen here. Product rule is going to happen here. And not only that, but I actually thought this was really sweet. Mark said to me when he looked at this problem, I really liked that question. What did you like about this question, Mark?
When we get our derivative, because of the product rule, I can already tell we're going to have an x and a y in our derivative. And Verge has only given us z and y.
Yeah.
So we do not know what x is when z is 3 and when y is a half. So we have to go find that out, and that's cool. And you got to watch out for that, right, guys? You got to, and also you got to realize there's a fourth variable hiding because everything's with respect to t.
Mm-hmm. So z is 3. So I'm going to go ahead and find my x right now as I'm thinking about it. So z is 3. I'm going to substitute that in, is equal to x, and then times y is a half. So a half squared. A half squared is 4.
A fourth, yeah.
A fourth, sorry,
Yeah.
I'm already multiplying in my head.
Oh,
exactly.
Yeah.
So then my x value that I end up getting is 3 times 4, which is 12. So I'm going to need that after I do product rule. So let's see if I can slide this down and do product rule up here. So z is equal to xy squared. So dz dt, the derivative of this expression with respect to time, is equal to x times the derivative of y, 2y dy dt, plus y squared times the derivative of x with respect to t is dx dt. And then it's a matter of substituting all those values in. So let's see, x is equal to 12.
Yep.
And
Y is a
then
half.
y is a half. That's going to work out nicely. dy dt is equal to, I got my little list here, 5 plus, and then y squared is
that's your
half
1/2 squared.
And then dx dt is -2. So I can go ahead and do all this arithmetic. In real life, I obviously do all this arithmetic, and I'm not going to do it right now.
Yeah. It ends up being 60 minus a half if you want to check yourself.
Yep, 59.5. Good. The biggest, I think, and we've kind of been building up to it, is the idea of these related rates problems, which are so delicious and my absolute favorite. And we're going to actually, for 4.5, which is technically the related rates section, we're going to do some really great free response questions in a minute.
I hope you get some email about using the phrase delicious.
Yeah. It's so tasty.
The choice of words. Sorry.
So Mark is going to do those free response questions with us, with me watching, obviously, and making sure that everything's good. But let me just do 2 last little examples for you. The 4.6 was about the tangent line approximation or linearization to approximate. So this is a very bare bones example, but given g of x is a differentiable function about which little else is known, other than g of 3 is 2 and g prime of 3 is 7, use the tangent line of g of x at x equals -3 to approximate g of -2.9. So I have my point, which is -3, 2, and I have my slope, which is 7. And I can write my tangent line, and you can write it the way Mark does, or you can write it the way I do. I usually use point slope with the y minus y1 on the left.
Tomato, tomato.
Tomato, tomato. So my tangent line is y minus 2 equals 7 times x plus 3. My advice to you would be to not distribute, to go ahead and See, now I really would move my 2 over at that moment. Go ahead and substitute in the negative 2.9 since we're using our tangent line to approximate. And then 2 plus 7 times this quantity is really your answer. You could go ahead and say 2 plus 7 times 0.1. Is that right?
And that's why you don't want to distribute, right? Because
Mhm.
that's always you're staying so close to your center or where your approximation is that addition or subtraction is going to be much easier than multiplying 7 times negative 2.9.
Yeah. And again, if you've done like 50 problems of these in your senior year or junior year or sophomore year, think about that. And we've probably done, you know, that times 30. So like, we know that this is the most efficient way to do it and least amount of mistakes. But again, this could be how you leave your answer if you want on the AP exam. Last one here is in this unit, L'Hopital's rule. The really sweet thing about L'Hopital's rule is that the way the AP asks L'Hopital's rule questions on free response anyway that we've seen has to do with fundamental theorem of calculus. So I'm just going to kind of like just do a little taste of it right now, but we're going to come back to this idea next week when we do when we review antiderivatives, definite integrals, that kind of stuff. Okay, so as I look at the limit as x approaches 5 of x to the 4th minus 625, all divided by x squared minus 25, if I do direct substitution here, I get 5 to the 4th minus 625, which is 0 in the numerator, divided by 5 squared minus 25, which is 0 in the denominator. So I get this indeterminate form of 0 over 0. So I could factor and cancel, which we did back on Monday. But if the limit of your numerator is going to the 0 and the limit of your denominator is going to 0, then L'Hopital's rule applies. If you have to justify it, you need to write down everything I just said. But when we're going to do that like next week or maybe even tomorrow. But for right now, I'm just going to tell you, and the L'Hopital's rule means that, hey, I could take the derivative of the numerator. If I've you know, explained the conditions, the derivative of the numerator, the derivative of the denominator, so 4x cubed in the numerator and then 2x in the denominator, and see what happens. In this case, I can algebraically simplify and say that the limit as x approaches 5 of 2x squared when I do some canceling out here, and I wind up with 2 times 5 squared, which is 50. So I just used L'Hopital's rule there to evaluate that limit. I could have factored and canceled. If I were asked to justify, I would have had to write everything down that came out of my mouth, okay? And we will do that maybe tomorrow, but definitely next week. So that's just a little like highlights
of Unit 4.
Highlights of Unit 4 in one page. And Mark's going to go ahead and steal the screen, and we're going to go ahead and take some carefully selected free response questions. Oh, but first he has to say some stuff.
And of course, as I steal it, I'm just showing you what the justification that Verge was talking about. That this is really probably the most concise way to say it is this is 0, which is also that, and therefore I can do that.
Would you have to say that therefore L'Hopital's rule applies, or can you?
You don't have to name. You never have to name the theorem. Yeah, if I was doing it myself, I would have written this and then said therefore this equals that. But I was trying to fit myself in the space.
And we will write up those justifications. And not just show them to you, but actually write them out and talk them out with you.
We're not.
We got so much time. So much time.
Yeah, that's Verge made a good point. We were talking, trying to come up with our plan, and we're experienced teachers, but we're new to this format, obviously. And one of the things we talked about is as you're learning it as you go, that first year, and some of you have first and second year calculus teachers, and what's awesome is the bonding they're having with you guys is way beyond anything that they'll have again, because there's only a few of those first classes. But a lot of times, we're working 2-3 days ahead of you. And so we were talking about our plan, and Verge made a great point that we don't want you to peak too soon. Any of you that have been athletes or music or anything like that, you want your practice regimen to get you to peak closer to the exams.
Definitely. You don't need to be peaking right now, and the exam is basically 4 weeks away. You need to peak about 7 to 10 days in advance.
Exactly.
So, yep.
Okay, so a cylindrical barrel. This is from 2019 ABBC 4. These are labeled up on the top. We are not doing the entire problem. We're just doing the problems that are relevant to Unit 4, we felt were. And there's this rain barrel, obviously this highly detailed drawing, which they actually address down here. A cylindrical barrel with a diameter of 2 feet contains collected rainwater, as shown in the figure above. The water drains out through a valve not shown at the bottom of the barrel. The rate of change of the height, h, of the water in the barrel with respect to time is modeled by this differential equation, dH dt is equal to negative 1/10 of the square root of h, where h is measured in feet and t is measured in seconds. And by the way, the volume of a cylinder with radius r and height h is that the volume is pi r squared h. So they've given us a lot of information. And in A, they're saying find the rate of change of the volume of water in the barrel with respect to time when the height of the water is 4 feet, indicates units of measure. All right, so the drawing actually doesn't borrow or doesn't offer a lot of information for us, does it? I'm actually going to scoot this up so you can't see the barrel, and I'm going to bring in my work.
Actually, though, it does.
My camera just scooted. Oh no.
Actually,
Sorry.
Mark, I would say
what you
that
get when you $90 camera, what you get, what you pay for, right?
I would say that the rain barrel gives a lot of good information for part A. Oh, well, it's written there too, but it's actually on the figure.
Yeah, it is easier to see in the drawing, but they do give it all in here.
Okay, good.
And of course, that diameter of 2, the real thing we need, because we're looking for radius, is 1, right? So I'm going to bring that down. So now part A says find the rate of change. Oh, let me scoot that over. The imaginary, I have no idea how big that box is in the corner.
It looks good.
Find the rate of change of the volume of water in the barrel with respect to time. So I'm going to stop reading. Rate of change of the volume of water with respect to time. So rate of volume respect to time is what we're trying to find. When the height is 4. So, man, if only I knew the volume of a cylinder.
It's there, Mark.
Thanks for humoring me. It's given. All right. So I have a formula. I could take the volume, I could take the derivative right away. My only issue with taking the derivative right away is I have a product over here. Pi is not part of the product that I'm talking. It's not a product of the functions. It's a constant. So pi's along for the ride. But this r squared h, and I could do that as a product rule. It's very simple. But what do you notice about the radius down this entire shape?
It's never changing.
It doesn't change. It's constant. And since it's constant, I can plug it in ahead of time.
And this is very dangerous because that's the only time you can plug in a number before you take the derivative.
Yeah, because if it were changing, we're measuring rates of change and they're going to affect each other.
Correct. Yeah.
And that would be bad. But it's not this time. So I'm going to get away with it. And so we get V is pi h. And now I'm going to take my derivative with respect to t. The derivative of V is 1, but it's not a t. So I have to put a dv dt on there. And the derivative of pi h, if you think of that as basically 3h, right? The engineers, that's just 3h. The derivative is 3, spelled pi, dh dt. That was actually intentionally for one of my students this year who always rounded pi to 3 and always said it was his engineering friends had told him that was okay. All right, so I've got my dv dt, but it says they want to know it when the height of the water is 4 feet. I don't have anywhere to plug in 4, but we do have a formula for dH dt. So that is negative 1/10 square root of h times pi. And now if I want to evaluate that at 4, and of course I could stop right here, or I can simplify that. That's 2 over 10 or negative 1/5 pi. Units, it says indicate units. Well, how do we measure volume?
Cubic feet, cubic meters, cubic
feet.
yards.
So, and this was feet, right?
I think so, yeah.
I'm going up and looking 2 feet, yes. And then with respect to time, and time in this problem says time is measured in seconds. So feet cubed on top per seconds.
Mm-hmm.
Again, I'm just pulling my units right off of that. I don't spend a lot of time on that. All right, good with A?
Looks great.
Anything to add? Or
you can write out the word seconds if you want. You can write SEC if you want. Lots of different ways to.
Yeah, I would definitely avoid the little apostrophe for feet here.
Oh,
because I think that would be weird with the cube. But
yeah.
All right, so let's go to B. So now it says when the height of the water is 3 feet, is the rate of the change of the height. Ooh. Rate of change of the height of the water with respect to time increasing or decreasing. So I'm asking, the way I always do this, I say cover that up and say, it says, is that increasing or decreasing? Is the rate of the height, well, what is the rate? The rate of the change of the height with respect to t was the formula they gave me. And then they want to know if that is increasing or decreasing. And how would I find out if that's increasing or decreasing?
Sounds like you got to take a derivative to me.
Another derivative.
Yeah.
So we're going to take our derivative with respect to time. And I hear a good friend of mine has her kids memorize this. So they know that the derivative of the square root of h is 1 over 2 square roots of h immediately.
It's funny because I don't make them memorize it.
Sorry, makes a bad word. You're right.
But they actually,
yeah.
Because they've seen it in so many different areas, they say, well, can we just always just do that? Can we just always write that all the time? And I think that's an important thing to realize, that if you have proved something, then it's allowed to be used for all time, right? So yeah.
So this is just the thought bubble over here on the side. The derivative with respect to h of square root of h is that. But we're taking derivative with respect to time.
Yep. This is the biggie.
So there's a chain rule in there. That related rate is a chain rule. So because we're taking the derivative with respect to t, I do have to chain out that dh dt on the end. And then they want this evaluated at 3, so I could plug the 3 in, but I'm going to go ahead and substitute in that dh dt, which was up
negative
here,
1/10, yeah.
Negative 1/10 square roots of h. It's funny, I'm looking up at my screen. I actually have the paper sitting in front of me. And if I look at this, hey, these two guys know each other.
They can take each other out.
Negative times negative.
Positive.
1 times 1 times 1, 10 times 10 times 2. Turns out that the second derivative always equals 1/200th. And that's greater than 0. So what can I say?
You can say that dH dt is increasing because the second derivative is greater than 0. This is actually kind of slipping into analytic applications of the derivative a little bit, which is Unit 5, but considering we're reviewing, you've already done Unit 5.
We're using the related rate to get there, right?
Yes, absolutely.
So I didn't want to just stop and go, and we'll answer the rest next week.
No.
Yeah, so dH dt is increasing everywhere. So specifically at h equals 3 as well, right? And that's my justification, is my second derivative is 1/200th, which is positive always. All right. So now we're going to move to 2018. Just walking back in time, I guess.
True. That's true, actually. They're all kind of consecutive.
They're all number
backwards.
4. They're all number 4, and they're the last 3 exams. But I can guarantee for every single person watching, your version of the exam will not have a related rate on number 4.
Nope. Because there won't be a number 4.
There won't be a number 3 or a number 4.
Or 5 or 6.
All right. So we've got the height of a tree in meters. And this, by the way, you'll notice the stem's not here, that I'm jumping straight into part D. I told Verge this morning. I read this problem about 5 times last night. to say, yeah, the stem's not used at all. So I mentioned this the other day, keep the pencil moving, keep reading parts. This is completely a self-contained problem. The height of the tree in meters can also be modeled by the function g, given by g of x is 100x over 1 plus x, where x is the diameter of the base of the tree in meters. When the tree is 15 meters tall, the diameter of the base of the tree is increasing at a rate of 3/100ths of a meter per year. And according to this model, what is the rate of change of the height of the tree with respect to time in meters per year at the time when the tree is 50 meters tall? So there's a lot going on. Holy cow. But they want to know rate of change of the height. And this is the height. And this is the only reason the stem's important at all, I guess, is you're like, well, why'd they use G for the height? Because A, B, and C were about another function called H. And mathematicians typically, if we keep talking about the same topic, we'll just go ahead and go alphabetically. Oh, well, we did G, now we'll do H. Or we'll go the other way. I guess they didn't want to do I because capital I has all kinds of issues. All right, so we're going to be doing dg dt, because that's my rate of change of the height with respect to time. Oh my, what do we have here, Verge?
Low-de high, mine, high-de low, oh, low, low. Quotient rule.
You know, and I'm going to go through this pretty quick because we've done a few of these. But it's the derivative of the numerator, which is 100 times the denominator, minus the derivative of the denominator times the numerator, all over that denominator squared. And then, hey, these are all x's.
And we're differentiating with respect to t.
The dx dt had to show up.
When I did that problem, just FYI, I put that dx dt on each term in the numerator, and that's okay too, but take a look.
Absolutely. I just factored it off, right?
You put it out back.
Yep,
like
I just factored it. I just factored it out back.
Put it out back.
So, and x is the diameter, right?
Yes.
And they said the diameter is the 0.03. So that dx dt is the 3/100ths. And now all I have to do is plug in the diameter when the height is 50. I gotta cut that off. They didn't tell me the diameter when the height is 50.
Well,
so now we gotta do some more side work. So 50 is 100x over 1 plus x. I can multiply that 1 plus x over, get 50 plus 50x is 100x. You can also do this one by inspection. A lot of you could. That x is 1.
Yep.
Because 100 over 2 is 50.
Just slide your paper up a little teeny bit.
Yeah, okay.
Just a teeny bit.
So yeah, but 100 times 1 over 1 plus 1 is 50 as well. So I just do 100 times 1 plus 1 minus 100 times 1 over 1 plus 1 squared. And that looks like 200 minus 100 over 2 squared, which is 4. Of course, you could stop here, right?
Yep.
Use Verge's happy face. That looks like 25 times 0.03.
No, it looks like 100 over 4 times 3 over 100.
Hey, I like that.
And that's so cool.
Clever person goes, boom.
Yeah.
Did they ask for units? No, but I'm going to give them any. Oh, they gave them.
Yeah. If they ask for units, it's going to be worth something. If they don't ask for units, don't worry about it. Yeah.
Absolutely.
Yeah.
All right. Well, we got 2 minutes left. Do you want to talk about number 4?
Well, I think
the next number 4.
I think what I'd like to do is kind of talk about the fact that this is where we're going to start tomorrow. So I think it would be a really good idea. These are contextual applications. Context means with text, like con queso, with cheese. So it takes a while sometimes to digest all the given information. So if you do nothing before tomorrow's session, I would read this about 6 times and try and work it out. This was a very difficult free response question. Kids really stumbled on it. But these are doable problems. They truly, truly are. And we're going to start tomorrow after the warm up with this and then do some other free response questions. Is that good, Mark? I mean, like that, I think.
Yeah, I think that's
to
great.
Encourage them to get going on this.
And I think that as I switch my share screen here, I think that one of the things we should emphasize with that is when Verge says that it was a difficult problem, it was a difficult problem under the time circumstances, and that's why we're trying to get you practice now. It's not any harder than any of the problems we've done already, but as she said, that text and contextuality made it harder, and our job here is to help demystify some of that for you.
Yeah, and actually, you know, there's always great memes immediately after the AP Calculus exam, so you can look up the potato problem from 2017 and find some,
Yes.
find the memes.
One of my favorites that year that someone tweeted, a lot of them are on Twitter. You just go to Twitter and type in that.
Or maybe Reddit, I don't know.
Yeah. There was a tweet, some poor student who'd gotten the international form or the late form or something as a controlling factor, and said, when all the memes are about potatoes and bananas and you didn't see either. And it was just the monkey giving the side glance, you know.
Right. You had a different version, and that could happen this year as well, where there's a couple different versions pushed out, you know. So we don't know. That'll be interesting.
All right. Well, thanks for watching. Again, I've had this slide up for a second now, so you can use your camera to find that Dropbox or type in that bit.ly. It is in the description under. I promise. There's an arrow down there. It says show more. Scroll down. The kids know where the comments are. Text your teacher where to find it, so you can get to that Dropbox. What's in our Dropbox today, Verge? The notes.
We have the notes page,
the 3 free response, and a new circuit, right?
And yes, and it's
a circuit I wrote. It's everything up to implicit, so it's kind of a review of the week up till now.
Yes, it's to me, it's a little bit more doable than the chain rule circuit, where you can get kind of bogged down in a lot of algebra and trig. Mark's is really clean and quick. It would be a nice one to work on this afternoon.
Cleanse your palate before tomorrow.
Before you have a potato.
Again, information for the test. If you want to freeze the screen and get that website, freeze the screen, get that QR code or that bit.ly, and that takes you straight to the calendar. It's also in the top level of the Dropbox. All right. So thanks again.
Tomorrow's Friday.
There's music we can't use, huh?